In today's class, we're going to be talking about the reduction of carbonyls with hydrides. So hydrides are not delivered to you as a reagent where it's H-, but we can formally treat them as H- mechanistically. Again, that's a simplification of how these reagents really work, but for our purposes for mechanism, that'll work fine. Okay, so again we have carbonyls, so this is just a simplified carbonyl where it's carbon with a double bond to oxygen atom, and hydride, and you see that the hydride adds into the carbon of the carbonyl. That mechanism is very similar to the mechanism we've seen with Grignard reagents, or anytime we add a nucleophile into a carbonyl. So the nucleophile reacts with a carbon, the electrons from that double bond go up onto the oxygen atom, giving you a negative charge on that oxygen atom. So let's now look at what would happen when we have a few other things on that carbonyl, and you'll see in a moment there can be lots of different things. So if they are different, you wind up with now a new stereogenic center, so the resulting compound could be chiral. But keep in mind that this hydride could add from either face, so you'd likely end up with a mixture of both the front attack, as shown, and the product of the nucleophile approaching from the backside of this molecule. So if you have an aldehyde, for example acetaldehyde, reacting with sodium borohydride, the hydride adds in, and I'll go ahead and highlight where it adds in, and it gives you an alcohol, in this case a primary alcohol. So the carbon is bound to 2 hydrogen atoms, and alcohol, and again this is the reaction of acetaldehyde with sodium borohydride. This resulting product, you can remember, is called ethanol. If you try to treat a ketone, for example acetone with sodium borohydride, it also reduces the ketone with the same mechanism shown above here to give you now isopropanol. Again, you can keep track of that hydrogen atom or the hydride that was added into the molecule there. One thing to keep in mind with this mechanism is that you don't have to draw on these hydrogen atoms. So again, the normal way that you would draw ethanol, or the way you might see it on an exam, would be it drawn simply like this. So if I were asking for the reagent from acetaldehyde to ethanol, the reagent would be sodium borohydride. Let's look at some more stable carbonyls. So for example, an ester. And this is going to be true of all carbonyls that are more stable than esters as well. So if you think back to the stability trends of carbonyls, those stability trends are really important. So sodium borohydride, if it were to react with, in this case, an ethyl or methyl acetate, this ester, we would observe that there's no reaction. There could be a reaction, so you could heat up the reaction and really force it, but generally esters are thought to be, or are expected to be, not reactive with sodium borohydride. A solution to this is to use a more powerful reducing agent. For example, lithium aluminum hydride acts in a very similar way to sodium borohydride, so the first hydride adds into the carbonyl, the electrons pop up into this oxygen atom. Now, unlike ketones and aldehydes, you have this leaving group in the form of a methoxide, and that happens very, very quickly in solution. So you quickly kick off methoxide, and you wind up with an aldehyde, in this case, acetaldehyde. Now, if you look at acetaldehyde and its reactivity as compared to the starting ester, acetaldehyde is significantly more reactive, and so therefore it's going to take up another equivalent of the lithium aluminum hydride. It will steal effectively what you were hoping to react with the ester, and it will react to give you, again, like we saw on the previous page, the deprotonated oxygen, which would, upon workup, give you ethanol. So the thing to note here is that you can't, when you're using lithium aluminum hydride, you actually can't stop at the aldehyde. There are other ways of doing that, and we're not going to necessarily discuss that in this class, but there are ways of stopping at the aldehyde. It takes a different reagent. But again, if you add a lithium aluminum hydride to an ester, you're going to get all the way down to the primary alcohol. That's a really important feature of these reactivity. And actually, we didn't talk about this in the context of Grignards, but Grignards are the same way. Grignards can add into esters, but they add in twice. Let's look at how you might be able to predict that a reagent would be a reducing agent. Well, if you look at boron as compared to aluminum on the periodic table, they're right on top of each other. Boron is right on top of aluminum. So again, the telltale sign that you might have a reducing agent is you have either a boron or an aluminum atom bound to hydride sources. In this case, it has 4 hydrides on this one, 4 on this one as well. Only one of the hydrogen atoms acts as a hydride. The other 3 are just kind of there for the ride. The other thing to note about this is lithium and sodium are also related to each other. They are also on top of each other in the periodic table. So you can use your periodic trends and your knowledge of that to make inferences about how a reagent might work. So there are lots and lots of different reducing agents. We're only going to cover these 2 in this class. But for example, there could be a triacetoxy borohydride, so that you have 3 OACs and an H on a boron, and that's still a reducing agent. Let's look at an example that you might see on an exam or on a quiz. So if you had this type of molecule here, where you don't have to worry about the middle part, but let's look at there's a ketone and an ester. So those are the functional groups you have to keep in mind. If I were asking you to make this as your product, or if you were hoping to make this as your product, so you're only going to selectively reduce the ketone as opposed to the ester, you'd want to use the milder reducing agent, so you would use sodium borohydride. What if you used lithium borohydride? So think about that for a moment. What would happen? Well, you would reduce the ketone as you did before, but you'd also reduce the ester, and you'd reduce the ester all the way to the primary alcohol. So something to keep in mind when you're doing these types of reagents, while it is true that the ketone is more reactive than the ester, it is really hard to dose in the exact amount of lithium aluminum hydride and add it at the exact addition rate, so you only have reduction of the ketone in the presence of the ester. So typically chemists will choose a reagent that has selectivity built into the reagent itself. The common error for this type of process is to not think about the fact that you've added hydrogen atoms, and as a result, the common error is that losing track of your carbon count. So I'm going to show you on our starting materials and products. On the starting material, you have 3 carbon atoms on the top, 3 on the bottom, 3 shown here, and 2 where one of the 2 carbons is bound to the ester, and now you have 2 carbon atoms here. So you have not made or broken any carbon-carbon bonds. So again, you have to keep track of your carbon skeleton when you're thinking about these. Well, I look forward to any questions you have in class, and have a great rest of your day.